Okay. Um, Welcome everyone to the 103rd meeting of this seminar. Today our speaker is Martin Frankland from the University of Regina, and he'll be talking to us about Toda brackets in n-angulated categories.
Thank you. Well, first, I'd like to thank Ruder Deep for organizing the seminar, for the invitation. It's a great pleasure to be sharing this project with you today. This project is all joint with Sebastian, Martensen, and Marius Thaule from NTNU, and also in attendance. And let's get started. This will involve some n-angulated categories. I do assume that you're familiar with triangulated categories because that is in the title of the seminar series. But I don't assume that you're familiar with n-angulated categories. So let's start with that. Well, the idea is that the structure is very similar to a triangulated category, but you have longer triangles. So just right off the bat, n-angulated here has nothing to do with higher triangulations in the sense of multi-niotis with more coherence. Totally different ballgame. You just have longer triangles. So four-angulated category should really be called a quadrilateral-lated category, but we don't say that. They were introduced by Geiss, Keller, and Oppermann in this paper from 2013. And their main source of examples, and I'll get to that in a few minutes, was in some certain derived categories in representation theory, especially representation theory of finite dimensional algebras over a field, quiver representation theory. That's where you see that kind of structure that they noticed. All right, what is that structure? Well, actually, just maybe as a forward, if some of you like triangulated categories, but you don't care at all about the case n greater than 3, that's okay. You're still welcome here today. Stick around because I included 2 tidbits that are interesting, even in the case n equals 3. And we'll see that later on. The basic setup is the same. You start with an additive category equipped with an automorphism. I'm a topologist, so I use suspension notation, sigma, but if you're an algebraist and you prefer brackets 1, that's fine. This is an inclusive space. And n will be that length of the n angles. It's just some integer that's at least 3. An n sigma sequence is just a diagram of that shape in the category C. The case n equals 3 should be familiar because that's the shape of the distinguished triangles in a triangulated category. So we just allow them to be longer. Now a pre-n-angulation, pre-n-angulated category is equipped with a certain collection of those n sigma sequences that you want to be distinguished. And those are called the n-angles. And they should satisfy a few axioms that look a lot like the familiar ones from triangulated categories. Namely, that if you take a direct sum of n angles, that's still an n angle. If you take a summand as well, if you modify it by an isomorphism, that's still an n angle. Then you've got the trivial ones, just sticking an identity between 2 different positions and zeros elsewhere. That should be an n angle. And every map admits, I want to say co-fiber extension because I'm thinking of triangulated categories, but here they're not really co-fibers. They're just the longer version of that. But any map can be extended to an n angle. That's this next axiom. And you can also rotate them in either direction. And note the sign, if you're familiar, if you're used to triangulated categories, you're used to seeing the minus here, the minus sign once you rotate a triangle. For an n angle, there's a sign. So for a four-angulated category, you just see the suspension of F1. It depends on the parity of n. All right, what else do we know? We can fill in maps in triangulated categories. Those are the co-fiber fill-ins. But now, because those are not really co-fibers, you have a longer diagram. But you can always complete such a solid diagram to the dotted parts over there. So I think of that as a co-fiber fill-in because I'm a topologist, but it's just longer. And in fact, if you look at this list of axioms, it is exactly the list of axioms of a pre-triangulated category in the case n equals 3. So far, so good. But what about triangulated? So if you want to remove the pre, you need to assume the octahedral axiom. That's this extra axiom built into the definition. And for a pre-n-angulated category, we'll call it n-angulated, if it satisfies an analog of the octahedral axiom. Now, if you remember Niemann's work, he noticed that the octahedral axiom is equivalent to saying that any one of those fill-in problems admits a good fill-in, which means that the mapping cone is still distinguished. You can use that as your definition here of that axiom, and that was the original definition. But then it was reformulated by Peter Berg and Marius Thaule in a way that's more reminiscent of the original octahedral axiom of Verdier for triangulated categories. So that's available, but I will not make a big deal of that because, in fact, it's entirely irrelevant to my talk today. The whole talk, and in fact, the whole paper that we wrote is pre-n-angulated. We don't use the octahedral axiom at all. I suspect that you would need it if you wanted to work with higher Toda brackets, but for the version that I'll present today, we don't need the octahedral axiom at all. So let's just forget about it. Now, the main difference between the triangulated case and this n-angulated case is that cofibers are not unique, right? We're used to this fact with triangulated categories that if you take a map, its cofiber is well defined up to isomorphism. It's not the case anymore as soon as n is at least 4. For silly reasons, you just have more room to mess up the 4 angle in a way that changes the cofiber. So here's the simplest example. Start with a 4 angle and just mess it up by adding a trivial summand in positions 3 and 4. And well, that's a direct sum of n angles, of 4 angles, so it's still a 4 angle. And I haven't changed the first map, but I have drastically changed the cofiber object. So we just have to be very careful. Now, to work around that, you can impose some kind of minimality condition. There are some n-angle extensions that are better than others, but that requires extra work. It's just not a consequence of the definition. I mean, not with any n-angle. You have to be careful. And why do we care about that structure? Because there are examples, right? It would be a letdown if there were no examples. But in fact, there's a whole supply of examples given by this main theorem of Geiss, Keller, and Oppermann, where you start with some ambient triangulated category. Typically, it will be some bounded derived category of maybe some path algebra. I'll get to examples of that form later, but for now, it's just a triangulated category, but it has sitting inside it an n-2 cluster tilting subcategory that's closed under the n-2 fold shift suspension. The conclusion in that setup is that this cluster tilting subcategory has an n-angulated structure where the automorphism for the subcategory is that n-2 fold suspension of the ambient triangulated category. And I have to tell you what the n-angles are, and they are the diagrams of that form. It's a bit of a mouthful, but yeah, they're given by this condition where the last map that wraps around to the n-2 fold suspension is actually a composite of all these degree shifting maps down here. That notation, the little bar here, means degree shifting. So that's really a map to the suspension of what's written. And because there's -2 of them, when you compose them, the map really goes from xn to the n-2 fold suspension of x1. And that's this last step fn over here. And each of those is a distinguished triangle in the ambient category, triangulated category T, and those just commute. So distinguished, commutes, and so on. And the half objects here are allowed to be outside of C. They're in the ambient triangulated category. It's not obvious why this works. It's a, it's a theorem that requires a lot of work, but it is true. And we'll look at some examples later. But for now, let's just take that as the main reason to care about that kind of structure. I will provide examples, but just hang on. I want to talk about Toda brackets so that I can also present the brackets in the examples later. So what about the brackets? Well, if you've computed something in stable homotopy theory, you probably ran into some Toda brackets. They're an important tool for computing, say, stable homotopy groups of spheres. And the idea is that they arise from null homotopies. If you have composable maps where the twofold composites are null homotopic, you can pick null homotopies to witness that and assemble the null homotopies into a new map. Now, how do you witness that two maps in a row are null homotopic or composed to something null homotopic? You can exhibit that, you can witness that by picking a lift to the fiber of the second map or an extension to the cofiber of the first map. And because of that, well, yeah, there are different constructions of the Toda bracket. We start with these three maps in a row. Oh, yeah, I'm just going to review the triangulated case for now. And I'm recycling the notation or terminology from one of my previous papers with Dan Christensen. So here are different constructions of the Toda bracket. You can decide to focus your whole attention on the first map, extend it to a distinguished triangle, and then you witness the fact that F1 and F2 compose to 0 in the homotopy category by choosing an extension to the cofiber of F1. That's this phi right here. And then because F2 and F3 also compose to 0, you'll be able to pick this further map psi over there. And that psi is an element of that Toda bracket. All right, but why focus on F1? You can just dualize this construction, start from the end, F3, and then pick fibers. That's the iterated fiber Toda bracket. You focus your attention on F3, extend it to the left, and then exhibit or witness the fact that F2 and F3 compose to 0 by picking a lift to the fiber of F3. That's the gamma right here that witnesses that F2 and F3 compose to 0. And then again, because F1 and F2 compose to 0, you're able to pick this further lift, delta. And then suspending that will give you an element of the Toda bracket. Now, why focus on the ends of the diagram? You can also focus on the middle, F2. And then you get this more balanced construction that uses both lift to the fiber of F2, right here. That's the lift to the fiber of F2, exhibiting the fact that F1 followed by F2 is null homotopic. And the fact that F2 followed by F3 is 0 is witnessed by this extension to the cofiber of F2, right here. And then you patch them together, and you get your element of the Toda bracket. It's this composite that you see in the rightmost column. All right, a priori, it's not completely obvious that those are the same. And in fact, I think unstably, it's not. Well, because unstably, you really only have the two half triangulations, the suspension part and the fiber part or loops part. But in a stable setting, in a triangulated category, they are the same. They are equivalent definitions. And note that they're non-empty if and only if the twofold composites are 0. So two maps in a row compose to 0. Otherwise, well, you can't pick those lifts and extensions that were involved in the construction. Those are equivalent definitions. It's a well-known fact. It's classical. But when we looked for references, we found a few references in the literature, and they all use the octahedral axiom somewhere. That's because one inclusion is fairly easy. Let's see, the fiber cofiber included in iterated cofiber, I think is the easy inclusion. And then the harder part is the converse, and you can show that directly by invoking the octahedral axiom. And that's typically the argument you'll find in the literature. But it turns out to be a pre-triangulated fact. It does not rely on the octahedral axiom. So first tidbit that's interesting already for n equals 3. This classical fact about Toda brackets having equivalent constructions is actually a pre-triangulated fact. And one way to see this, and now that proof is in our paper, is by going through the explicit calculation that it just turns out to be a coset of the indeterminacy subgroup. The indeterminacy arises because of the choices. When I picked a null homotopy of F1 followed by F2, the different choices of null homotopy are really the maps here from the suspension of X1 into X3. And that's why changing that choice of null homotopy can give you a different element, and likewise for the other one. And so the choices involved in the construction give you those different possible elements in the end. All right. Now let's move on to higher n. Now that we're all comfortable with a triangulated, pre-triangulated case, what about pre-n-angulated? Well, let's try to play the same game. For 2 of the 3 constructions, the analog is pretty straightforward. You just copy-paste the definition and make the diagrams longer. Those are the extreme choices where you decide to focus your attention on the first map or the last map. The one in the middle is more subtle. The one that focuses on the middle map can be generalized in 2 different ways. Either you just center your attention on one of the maps somewhere, that will work. Or maybe more interestingly, you involve all of the intermediate maps. Both will make sense, and let's spell out how that works more precisely. So first, the setup, we're just going to be looking at n composable maps in a pre-n-angulated category. And we're trying to make sense of the Toda bracket by mimicking the triangulated definition. It's going to be still a subset of this Hom abelian group right here, where I need to suspend the domain. Let's start with the 2 extreme cases. If I focus my attention on F1, well, I pick some n-angle extension. It exists. And then I try to pick some cofiber extensions. I'm a topologist, so I think of them as cofibers. They're not. But just for psychological reasons, let's think of them as some kind of cofiber fill-ins. You can do that successively. And in the end, you get this psi, which is an element of that Toda bracket. All right, if we dualize this construction, same deal. You focus your attention on the last map, Fn. Take an n-angle extension to the left. So take fibers and then pick lifts to fibers like so. Those are the gammas. Do that a couple times and you end up with this map delta here. And then suspending it will give you an element of the Toda bracket. So far it's really copy-pasted, but just with larger diagrams. Where things get more subtle is for generalizing the fiber cofiber. Oh, actually, yeah, right there, we noticed that we chose the extreme positions, but you could also center your attention on F2 or F3 or F4 or F5. Just pick any of them. And those are what we call I-intermediate Toda brackets. They're obtained the same way, but by focusing your attention on Fi, pick an n-angle extension, and then use a few cofiber extensions on one side and a few lifts to fibers on the other side, and you patch them together. But writing that all in a single diagram takes some space, so I'll get ready. All right, here it is. Here's my map Fi. I picked an n-angle extension, which is this row. And then to its left, I use fiber lifts to fibers. On the right, I use cofiber extensions, and then I patch them together by suspending that and then composing. So it's really just interpolating between the 2 extreme choices. The more subtle construction is to try to involve all of the intermediate maps, which you can do. That's what we call the fiber-cofiber definition. And it's obtained by picking an n-angle extension of F2 and F3 and F4 and F5 and so on up to n-1 and connecting them all together. That also requires a very big diagram. Get ready. Here it is. There we go. So F2 is right here, and it has its chosen n-angle extension. F3 is right here. It has its own n-angle extension. F4 is here with its n-angle extension, and so on. Got this staircase pattern. And the maps we care about are those in the rightmost column. Take those and then compose them, and that's an element of the fiber-cofiber Toda bracket. So I know it's a lot to take in at once, so don't worry too much about the specifics. It's just some big diagrams. But the point is that they generalize the triangulated constructions. And one might hope that they all agree. It's true with a caveat. Well, first, just to digest this big diagram, let's specialize to n equals 4. You've got your 4 maps in a row. You'll use four angle extensions of the middle two, F2 and F3. And then this staircase diagram connecting them all. And this composite right here is an element of the fiber-cofiber Toda bracket in that case. All right, big diagrams. I like diagrams. So far, so good. But now, how do we argue that they are the same? Well, now we need to explicitly assume that the twofold composites are all zero. In the triangulated case, if that was not satisfied, all constructions were automatically empty. So there was no issue. Here we do have to assume that. And in that case, it's true that all the constructions that I just presented are the same. And so I don't need the decoration. I can just call it the Toda bracket. So no more subscript. It's just the Toda bracket. And all of those constructions will give you the correct formula. And again, we can be more explicit. They're all cosets of the indeterminacy subgroup. And the indeterminacy subgroup is similarly defined. You get to pick an arbitrary map in here and post-compose with the last map Fn, or pick any map in here and pre-compose with the suspension of F1. And those are, choices involved in the construction, and changing the choices will change the element by an element of the indeterminacy. So you get a coset. And that's actually how we prove it. It's by showing that those are all equal to the same coset of the indeterminacy. At first, we were trying to mimic the proof that uses the octahedral axiom. And I'm pretty sure we have a complete proof or something close to a complete proof for the case n equals 4. But already that requires a lot more work. It's much harder. And it doesn't obviously generalize to higher n. So that's why we switched to this point of view of just using the description as a coset of the indeterminacy, which makes the argument much easier. And this is the caveat that if some twofold composite is not zero, it could still happen that one of those brackets is non-empty, although the fiber-cofiber one will automatically be empty. So I would say that morally, the fiber-cofiber is the correct definition. And the content of the theorem is that those other easier constructions happen to give you the correct answer. But the fact that they might give you a wrong answer here is just for silly reasons. It still boils down to the fact that if you focus all your attention on F1, say, with the iterated cofiber construction, there's plenty of room on the right to mess things up and create some non-interesting example of that bracket. I view that as just an artifact, or it's a defect of those other constructions. So fiber-cofiber is really the correct one in my view. All right, so we'll just focus on the case where this chain complex condition is satisfied, the twofold composites are zero. I promised some examples. Let's start with a warm-up example. Let's look at finitely generated free modules over Z mod 4, or in fact, Z mod p squared when n is even. That's fine. If n is odd, you really want to take p equals 2, so just Z mod 4. And the automorphism is the identity. That may be familiar because it is the exotic triangulated category that Muro, Schwede, and Strickland produce. They constructed this triangulated structure on the category of finite free Z mod 4 modules with the identity as the suspension. Well, it's exotic in the sense that it doesn't come from some stable model category. In particular, it's not algebraic. And Peter, Berg, Jasso, and Marius, Thaule generalize this construction. Well, maybe I shouldn't say generalize because there's no obvious notion of being a topological n-angulated category. So they just constructed some analogous exotic n-angulation that is not algebraic. And it's fairly similar in its construction. Let me just spell out this example. If you take n equals 4, then because n is even, I'm allowed to pick any prime p. I'm not forced to take p equals 2. That's the business with the sign. The sign rules change depending on the parity of n. So here you can pick any prime p. And let's look at this diagram. It turns out to be one of the n angles, actually. And when you compute the total bracket, you end up with this set. The total bracket of this diagram right here is just the coset of multiples of p shifted by 1. So anything of the form 1 plus p modulo p squared. And now this is not a coincidence. We started with a 4 angle, and we see the identity in the total bracket. So that's foreshadowing for a few slides from now. All right, let's move on to a more substantial example. I mentioned that the motivation was coming from quiver representation theory, and let's see how that works in practice. All right, let's start with this quiver. So as a quiver, it's just an A4 quiver, but we impose a relation. We say that the path of length 3 from 1 to 4 should vanish. That's the relation. In other words, J here is just my arrow ideal, the two-sided ideal generated by paths of length 1. Its cube is the two-sided ideal generated by paths of length 3, but in this case, there's not much room for paths of length 3. It's just killing the path from 1 to 4. CBA, that's this path there. So we're killing that. And the quotient is a path algebra for this quiver with relations. K is just some base field, doesn't really matter here. And then we take modules, well, finitely generated modules, that's my lowercase mod is finitely generated. Right gamma modules. I mean, they're just the representations for that quiver with relations. And there are some interesting objects in there. I'm using this notation where I indicate where there's a copy of the base field K. So for instance, this notation 1, 2 says that there's a K in positions 1 and 2, and you stick an identity wherever possible. Those are the rules of the game for this notation. So for example, this 2, 3, 4 has a K in positions 2, 3, and 4, and identities between them. And this map, for instance, from 3, 4 to 2, 3, 4 is just including the end of that interval into a longer interval. And likewise, 1, 2, 3 going to 1, 2 is just modding out this copy of K in position 3. So those are the maps you see displayed in this big diagram. And why are some of them circled? Well, it turns out that they live inside an interesting cluster tilting subcategory. And if you take the direct sum of all those encircled modules, gamma modules, that is going to be a two-cluster tilting module in the sense of Iyama. So this is the condition. Add M is the additive closure, which means that you start with M, close it up under direct sums and summands. That's the additive closure, and it's going to be exactly given by those two collections of objects. It's some kind of orthogonality condition. And if you look at the projectives, well, yeah, you can start with a generator in degree 1 and propagate it forward. You get this projective module like so. And if you start in position 2, you get this projective module here. If you start in position 3, you get this module, and in position 4, those are projective, and the injectives roughly are given by propagating backward. So this quiver representation here is injective, start in position 1 and propagate backward. If you start in position 2 and propagate backward, you get this one. Here you get 1, 2, 3, which is also projective, and here you get 2, 3, 4, which is also projective. All right. And what does that buy us? Then you can run a few calculations, compute the projective dimensions, simple modules, and you conclude that the global dimension is 2. The longest projective resolution you might need has length 2. And then using some tools from representation theories, I'm sweeping a lot under the rug, you end up with a four-angulated structure on this subcategory of the bounded derived category. Now we're in the derived world. Everything so far up to the previous slide was in the additive world, the abelian world. Now this is derived. And in there, you stick M in a single degree. Think of a chain complex having M just in that single degree. That's this notation. It's a tiny chain complex. Here I'm using the algebraist notation of brackets to shift a chain complex. And then close it up under direct sums and summands. That's the additive closure. It gives you a subcategory. It's additive, and it is in fact the two-cluster tilting subcategory of interest. And just to give you a flavor of the four angles, some of them have, so the interesting ones have this shape. They're related to extensions, but yeah, it's not completely obvious. So I'm just going to say, if you sit down and start computing a lot of things, you can make everything quite explicit. In particular, you can start computing some Toda brackets very explicitly, and just for fun, we computed this one and concluded that, well, it's the whole Halm abelian group in this case. It's not, maybe it's a bit hard to follow on slides online, but if you want to see the details of the calculation, I will refer you to the paper. We include a lot more details. The point I want to make is that if you have your favorite quiver, you can start computing things very explicitly and making both the n-angulation and the Toda brackets quite explicit. That's the point of this example. Oh, and as a sneak preview, if you look at the paper, we also have a bigger quiver. So if you're into that stuff, don't miss out. Go look at the bigger quiver. It's quite lovely. All right, let's look at a few results about higher Toda brackets. Well, they're not higher, they're longer Toda brackets. We're in the same setup as before. We have our n composable maps, and we assume that 2 maps in a row compose to 0, because that's really the only interesting case. Well, there's a bunch of formulas that look like the juggling formulas from Massey products that you might be familiar with. For instance, how are the brackets related to the additive structure? You can add maps, and how does that behave with respect to the brackets? There's a list of formulas. There we go. Typically, you have these inclusions and not equalities. That's the sub part of sub-additivity. It's saying that you might get a strict inclusion. So just be careful. You want to say that they're equal, but they're just not. In some cases, they are. So if you're in the bulk, in the middle of that sequence of maps, things are safe. It's around the edges that things get dangerous, and you could get a strict inclusion. And yeah, you can pull out negative signs. That's always fine. All right, what else do we have? Well, you can also compose maps. And there you get more juggling formulas. Yeah, those are the actual juggling formulas in the literature because it looks like you're juggling the maps by moving them in and out of the bracket. Those are the formulas. Again, it's mostly inclusions. You get equality if you're in that safe zone in the middle of the sequence. But in general, these inclusions can be proper. So just be careful once you juggle those symbols. And here's that second tidbit that's interesting already for n equals 3. That gives us a nice collected reference for all those juggling formulas for threefold Toda brackets in triangulated categories. There are many good references for Massey products. There's way more literature on Massey products in the homology of the DG algebra. May's classic paper on matrix Massey products is a good reference. Ravenel's Green Book also has an appendix on Massey products. Isaacson's Dan Isaacson has some papers with a lot of those formulas. But for Toda brackets, the formulas are more scattered. There's a few here and there. So at least now, as a service to the community, we have them in one place if you're willing to specialize to n equals 3. Oh, actually, Dan Isaacson also gave a seminar talk that's available online that had a beautiful list of equations, but we just felt like citing a YouTube video is bad practice. So now there's a written reference. What else can we say about Toda brackets? Well, they satisfy this condition here. That's a condition that we use a lot in the triangulated case, right? That if you hom from an object or into an object, you'll get an exact sequence of abelian groups. Let's call that being Yoneda exact. Well, because it's saying that if I apply the Yoneda embedding to that whole sequence in C, I get a sequence of pre-sheaves of abelian groups, and it's exact. So this is literally saying that I get an exact sequence of pre-sheaves once I apply Yoneda. What you might wonder, well, does that characterize the n-angles? Well, it doesn't, right? N-angles do satisfy that. That was proved by Geiss, Keller, Oppermann. The missing bit is given by Heller's theorem. Heller observed in the 60s that to characterize whether or not this n sigma sequence, or I guess 3 sigma sequence in the classical triangulated case, to characterize whether or not it's distinguished, well, you need the Yoneda exactness. It's a necessary condition. It's not sufficient. The missing bit is that the Toda bracket here should contain the identity. So that was this little example. The exotic example had the identity in the Toda bracket for that reason. It was already an n-angle. And in fact, this proof that works for the triangulated case pretty much goes through for higher n once you have a few facts that were worked out by Geiss, Keller, Oppermann. So we just reap the benefits of their work and observe that this is true in general. In other words, the Toda brackets determine the n-angulation. What else? Yes, if we go back to this main source of examples in the theorem of Geiss, Keller, and Oppermann, the n-angulated category lives in an ambient triangulated category. So you could also talk about higher Toda brackets in the triangulated category. That's a much more complicated construction. It's some inductive process, and it involves some filtered objects that goes back to Joel Cohen and his work on the decomposition of stable homotopy. He introduced this notion of filtered objects, and it's quite involved. But it's available. You might wonder, well, are they related? And yes, indeed they are. If you have this Geiss, Keller, Oppermann setup, triangulated category, cluster tilting subcategory in it, and you take n composable maps in the subcategory. On the one hand, you can compute the Toda bracket that I defined a few minutes ago. That's the left-hand side. On the other hand, you can compute the higher Toda bracket, the complicated one, using filtered objects in the triangulated category, and they're equal up to a sign. The sign is an artifact of the conventions, but He computed it, and that is the precise sign. So the content of this theorem is that if you want to compute this complicated higher Toda bracket that happens to live in the cluster tilting subcategory, then you can use the n-angulation as additional tool that's much simpler to compute, and it gives you the correct answer, the left-hand side. All right. Now we can combine that with work of Jasso and Muro. In fact, much of this story of Toda brackets in cluster tilting categories was really initiated by Jasso and Muro. They computed some Massey products. They were looking in particular at the case where you have a DG enhancement, and they showed a theorem of the form Toda equals Massey in the case of an enhanced n-angulated category. In other words, you can compute the Massey product using the enhancement. Now you're in some chain complexes, some Halm complexes in a DG category. You can make sense of Massey products. Or you can use the higher Toda brackets using the triangulated structure, and they show that those are equal up to a sign. That's the Massey equals Toda. So by combining that with our theorem saying that higher Toda equals longer Toda, well, we get this formula. If you want to compute some Massey product, it's a mouthful, but it's just saying what DG enhancement means in this case. It means that you've got this DG category A in the background, whose homotopy category, well, such that, yeah, the homotopy category of A modules has this ambient triangulation, and sitting inside it, you've got a cluster tilting subcategory. Yeah, so the point is just that U is n-angulated. It sits inside an ambient triangulated category. And on top of that, you've got a DG enhancement in the background. So you can compute the Massey product using the DG enhancement. That's my left-hand side here. And then the right-hand side is the Toda bracket in the n-angulated category, as defined a few minutes ago. There we go. And let me conclude just with a few thoughts on where to take this, or some maybe future problems, or an invitation to everyone in the room to think about those things. Well, I'd like to see more computations and examples, applications. As a topologist, I would especially love to see more sources of n-angulated categories in stable homotopy theory. It's looking like there might be some examples related to module spectra over ring spectra with sparse homotopy groups. There's some work that suggests that, but it hasn't been worked out, so it's something to think about. Or maybe more algebraic examples that would also be interesting. Or maybe you can use those brackets that we defined to compute something else that you want, maybe some Massey products, maybe some X groups somewhere. Those are the kinds of applications I would like to see. And of course, as a homotopy theorist, a more fundamental question is, well, do those n-angulated categories admit a homotopical interpretation, just like triangulated categories are really the structure you see in the homotopy category of a stable infinity category? Is there some kind of statement like that? If an infinity category satisfies blah, 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 then its homotopy category has a canonical n-angulation. I would love to see a theorem of that form. Several people have thought about that problem, and it seems to be quite hard. There's no definitive answer so far. It doesn't seem like the first guesses work out. Maybe the answer turns out to be no. Maybe it really is just a specific structure that you see in those cluster tilting subcategories. Settling that question would be interesting as well, either way. But in particular, if there is some homotopical interpretation, are the Toda brackets some obstructions? Because in the classical case, let's think even unstably, if you have a sequence of maps of spaces, pointed spaces, such that the twofold composites are null homotopic, so a chain complex in the homotopy category, the Toda bracket is exactly the obstruction to rectifying that to a sequence of maps whose twofold composites are strictly zero. And I would love to see an obstruction theoretic description of brackets. We can also combine longer brackets with higher brackets. So far in this talk, I just talked about the n-fold Toda bracket in an n-angulated category, but you can also have more maps. So for instance, in a 4-angulated category, you can take 5 maps or 6 maps or 7 maps in a row. The definition is available. It exists. It's just an inductive procedure mimicking the way you define higher Toda brackets for triangulated categories, but it's quite involved. And working that out, I think, would probably rely on the octahedral axiom somewhere. At least based on my previous work with Dan Christensen on the triangulated case, I'm pretty sure that you would need the octahedral axiom in that setup. So that's something else to think about. And then something else is that I also worked on with Dan is that the atom spectral sequence is closely related to Toda brackets in the sense that the differentials can be written as certain Toda brackets, some higher order cohomology operations. And it would be nice if there were an analog for n-angulated categories. There's some interesting work of Giannis about the about Adam's resolutions. So he works out Adam's resolutions and works out a few of their properties. Currently, Marius and I are thinking about this question. Well, can we jazz that up to a full-blown spectral sequence? And then are the differentials somehow related to Toda brackets? It's just something we're curious about, but it's work in progress. We don't have any definitive answers yet. Thank you for your attention.
Thank you, Martin. Let's all give the speaker a round of applause. If you have any questions for the speaker, please ask them now. At the very end, you mentioned this work in progress with Marius about this atom spectral sequence question. So are you saying that you don't yet know whether you get a spectral sequence, or that you do know, but
Right. So the first step is to generalize the triangulated atom spectral sequence. That goes back to Brinkmann from the 60s, but a nice, maybe modern treatment is in Dan Christensen's Ideals and Ghosts paper from 98. Generalize that to the case where the projective class, which tells you which resolutions are allowed, is not stable. Because if you look at this work of Giannis, what he looks at are certain derived categories that appear in representation theory. And he looks at things like ghost maps, and that is actually a projective class, but it's not stable. Stable means it's closed under suspension and desuspension. But because in that business, what's really interesting is, say, two-fold suspension or three-fold suspension or four-fold suspension. What you end up with is this projective class that's closed under maybe a two-fold suspension, but not a single suspension. And he works out some of the groundwork. He describes what happens with these unstable projective classes, and he defines Adam's resolutions. And he works out a few basic properties, but he doesn't quite come out and say, oh, well, then you get a spectral sequence. So that's maybe the first step of our project in progress, is to try to cleanly work out what the spectral sequence looks like. Say if the E2 term has a nice homological description, say something about convergence. So that's more groundwork. But then what we want to get to is to specialize to this Geiss, Keller, Oppermann setup and see if the atom spectral sequence computed in the cluster tilting subcategory can somehow be expressed in terms of the n-angulated brackets. So the philosophy is the same, is that in the ambient triangulated category, you have a bunch of structure. In particular, you have the atom spectral sequence. And now the kind of theorem we're looking for is that, oh, well, this complicated structure can be expressed in a simpler way because you happen to be in this cluster tilting subcategory. That's the goal, but we're not we're not there yet. We just started thinking about that, but I hope that cleared up the roadmap.
Okay, thank you. Any other questions? Yeah, I don't see any more questions coming in from anybody else. Well, if we don't have any more questions, let's thank Martin once again.
Thank you.
So we won't have a talk next week. The week after next week, we will have Beren Sanders' PhD student, Changkan Ju, giving a talk on one of his papers. So I hope to see you there. Bye-bye.
All right. Thanks, everyone. Thanks for the deep.
Bye.
Bye. Thank you. Bye.